Abstract algebra is the study of algebraic structures that are defined in terms of operations, rather than specific numbers or objects. A group is a set G together with an operation that satisfies four properties: closure, associativity, identity, and invertibility. Examples of groups include the integers under addition, the non-zero real numbers under multiplication, and the symmetries of a geometric shape. A subgroup H of a group G is a subset that is itself a group under the same operation. The order of a subgroup is the number of elements it contains. The order of an element A in a group G is the smallest positive integer n such that a to the power of n equals e, where e is the identity element of G. If no such n exists, then the order of A is said to be infinite. A cyclic group is a group that is generated by a single element, called a generator. If a group G is cyclic, then it can be written as G equals a to the power of n and z, where a is a generator. A ring is a set R together with two operations, plus and, that satisfy the following properties. 1. R is an abelian group under addition. 2. Multiplication is associative. 3. Multiplication distributes over addition. And 4. There exists a multiplicative identity element 1. An integral domain is a ring that has no zero divisors, i.e., if AB equals 0 for A, B and R, then either A equals 0 or B equals 0. A field is a commutative ring that has a multiplicative inverse for every non-zero element. Examples of fields include the real numbers, the complex numbers, and finite fields. A vector space is a set V together with two operations, plus and scalar multiplication, that satisfy certain axioms. Examples of vector spaces include the set of polynomials, the set of functions, and Euclidean space. A linear transformation is a function t, v, greater than w between vector spaces that preserves addition and scalar multiplication. i.e., tu plus v equals tu plus dv and t2 equals ctu for all u, v and b and c in the field. The rank nullity theorem states that if t, v, greater than w is a linear transformation between finite dimensional vector spaces, then dim v equals rank t plus nullity t, where rank t is the dimension of the image of t and nullity t is the dimension of the kernel of t. The determinant of a square matrix A is a scalar that encodes certain geometric properties of A, such as its volume scaling factor and its orientation reversing behavior. The determinant is defined recursively in terms of minors and cofactors. An eigenvector of a matrix A is a non-zero vector x such that x equals lambda x for some scalar lambda, called the eigenvalue. The set of eigenvalues of A is called the spectrum of A. The eigenvectors and eigenvalues of a matrix are important in many applications, such as linear dynamical systems and quantum mechanics. A polynomial ring is a ring of polynomials with coefficients in a given ring. Polynomial rings are important in algebraic geometry, number theory, and other areas of mathematics. The division algorithm for polynomials states that any two polynomials fx and gx with gx not equal to 0 can be written uniquely as fx equals qx plus rx, where qx and rx are polynomials and the degree of rx is strictly less than the degree of gx. A field extension is a field F that contains a smaller field K as a subfield. Field extensions are important in algebraic number theory, where they are used to study algebraic numbers and their properties. Galois theory is the study of field extensions and their automorphisms. Galois theory provides a way to determine which polynomial equations can be solved by radicals, i.e., by using addition, subtraction, multiplication, division, and nth roots, and to classify the symmetries of algebraic objects. A module is a generalization of a vector space over a ring. Modules are used to study algebraic structures that are not necessarily commutative, such as groups and rings. Examples of modules include abelian groups, rings, and vector spaces. The tensor product is a way to combine two modules into a new module. Tensor products are important in algebraic topology, where they are used to define homology and cohomology groups. Category theory is a branch of mathematics that studies the properties of mathematical structures and the relationships between them. Categories are a way to formalize mathematical structures and their relationships, and are used in many areas of mathematics, including algebra, topology, and logic. Homological algebra is the study of algebraic structures and their homology and cohomology groups. Homological algebra provides a way to study algebraic structures by analyzing their exact sequences and derived functors. Group actions are a way to study the symmetries of mathematical objects, such as geometric shapes, algebraic equations, or functions. A group action is a way for a group to act on a set, preserving its structure and properties. Representation theory is the study of groups and their actions on vector spaces. In representation theory, groups are represented as linear transformations on vector spaces, allowing us to study their properties through linear algebra. The symmetric group is the group of permutations of a finite set. The symmetric group has many interesting properties and is an important object of study in algebraic combinatorics. The dihedral group is the group of symmetries of a regular polygon. The dihedral group has important applications in geometry, crystallography, and physics. The Sylow theorems are a set of theorems in group theory that describe the structure of finite groups. The Sylow theorems are important for understanding the structure and properties of finite groups, and are used in many areas of mathematics and science. Commutative algebra is the study of commutative rings, which are rings in which multiplication is commutative. Commutative algebra has applications in algebraic geometry, number theory, and other areas of mathematics. Algebraic geometry is the study of algebraic varieties, which are sets of solutions to polynomial equations. Algebraic geometry provides a way to study geometric objects using algebraic tools, and has important applications in number theory, physics, and computer science. The Langlands program is a set of conjectures in number theory that connect algebraic objects, such as Galois groups and automorphic forms, with analytic objects, such as L functions and modular forms. The Langlands program has important applications in many areas of mathematics, including algebraic geometry, representation theory, and harmonic analysis. Commutative algebraic geometry is the study of varieties that arise from commutative algebraic objects, such as commutative rings and algebraic schemes. Commutative algebraic geometry provides a bridge between algebraic geometry and commutative algebra, and has important applications in number theory, coding theory, and cryptography.